Hello class. So in this video, we'll continue on section 3.7. In the previous video, I gave you or showed you a simulation of our spring mass system. Right? So what happens when we have the setup, right? Again, with the assumptions that we have a simple harmonic motion, which is always given. 2, that we have free vibrations, and that we also have no damping. Right? So those are the 3 assumptions. Given those assumptions, I showed you how this spring mass system would work if we were in a given scenario, right? So in the scenario we saw in the simulation, we pulled on the weight. So the weight at first, spring mass system is at equilibrium. So the weight stretches the spring a certain amount and then it reaches an equilibrium state. Then in the simulation, I pulled two more units, right? So it's not an equilibrium anymore. And then we let go. And then we saw how the spring mass system behaved. Right? So we saw that all in the previous video. So hopefully with the explanation in the first videos in this section and that simulation, you can understand exactly what's happening. Right? What is it that we're trying to model? Right? What the motion looks like in this particular case. So now that we did that, let's actually go ahead and find the general solution to our ODE. Right? So in the previous video before the simulation, we had this differential equation that we found, right? Where K is the spring coefficient or the proportionality coefficient that comes from Hooke's law. M is the mass, right? T is greater than or equal to 0, right? Where T equals 0 is starting out either when we let go, if we have 0 initial velocity, or we push and pull on the weight when we let go, in which case we do have initial velocity. Right? The initial position is just wherever we let go, right? In the example of the simulation, I let go 2 units below equilibrium, so that would be x naught equals 2. Right? Because again, anything below equilibrium is positive position. Anything above is negative. And then x prime of 0 is x1, which again is the initial velocity. It's 0 if you just let go, and it's not 0 if you push or pull. Right? So those are the assumptions that we had, and then that's the differential equation we got. X double prime equals negative k over mx. So we're going to find the general solution. We're not going to worry about the initial conditions right now. We just want to find the general solution to the differential equation. So let's go ahead and do that. First, let me rewrite this in the way that they rewrite it in the book. Okay, so in the book, they'll rewrite this like this. So do x double prime plus k over mx equals 0. And then they'll rewrite it as x double prime plus omega. So it's a Greek letter omega. We already are working with 2 Greek letters, alpha and beta, which are well known, so I don't mind using those. Omega is not as well known, so instead of calling it omega, I'm just going to call it w. Right? So plus w squared, x equals 0, where what is w? Well, w is the square root of k over m. Right? So if w is the square root of k over m, then w squared is k over m. Now, the reason why we rewrite it like this, it's not maybe entirely obvious as of now, but it'll be entirely obvious when we actually find the general solution. And also, it's going to be nice when we find the general solution in more general cases, like when we include damping and when we include forces that affect the oscillations of the system. Now, one thing to note here, remember that this K, as I mentioned, comes from Hooke's law. Right? So F, or the restoration force K, so let me call it F sub K, is proportional to the amount the spring is elongated. Right? And remember, proportional meant a scalar multiple of that, so that's where we got Ks, right? Where S is the amount elongated. Okay. So we didn't attach any sign to K, and as I mentioned, the sign of K always is going to come out of the context, right? However, we can actually tell that K is always going to be positive. And I'm talking about this because I want you to see that K here, that W is actually a real number, right? It's not a complex number. So how do I know this? Well, I know this because, let me do this here. Let's say we stretch a spring 2 units, right? There's going to be a force. And that's going to be proportional to 2 times K. Now, the force, we usually just want to take it as, so it could have a sign, right? Meaning that if we stretch the spring or meaning that if the force is pushing upward, in our case of our example, this would be a negative force. However, we're mostly going to be interested in the magnitude, right? Meaning that in most of our applications, we're going to set this equal to the weight of an object, right? So some weight. And since weight is always positive, when we solve for K here, K is going to be positive because it's a ratio of two positive numbers. Okay. Now, two or however much we elongate the string, that is always going to be positive because we're interested in the displacement. So it doesn't matter whether it was a positive or negative displacement. What matters is how much was the spring elongated or stretched. Right? So this quantity S is also always going to be positive. So that's another way you can think of this. Positive number S, right? Right. So 2 times K, where 2 is positive. Right? So divide the weight by 2, or S, where S is positive. Weight divided by S is always positive. Right? So for our purposes, K is actually always going to be greater than 0. But again, this is not something that I'm forcing. This is just something that is coming out from the system itself. Okay. So again, I go over this now because I want you to see that this is actually a real number. Okay, so now that we have that, let's go ahead and find the general solution. Okay, so just a little bit of discussion there about that. Okay, so it's constant coefficients, linear, second order. We can't use integrating factor, but we can use the characteristic polynomial. Let's just go ahead and do that. So the characteristic polynomial in this case is going to be r squared plus omega squared equals 0. Right. Characteristic polynomial is r squared plus w squared, set it equal to 0 to solve for r. R squared equals minus omega squared, or w squared if you're saying omega. So r equals plus or minus the square root of minus w squared. Okay. W squared is always a positive quantity, right? So what does that mean for us? Well, we have a positive quantity times I times the square root of negative 1. Okay, so we can write this as plus or minus square root of w, and then we remove the I. Right? So we did this a couple of sections ago, right? I is the square root of negative 1, so we write it like this. Oh, and it should be w squared. Right. Finally, the square root of w squared is plus or minus w. Right. We have a plus or minus in front, so we already took care of that. So if we simplify this, this becomes just plus or minus wi. And you don't have to write this in terms of w. Again, I'm going to be doing it because that's how they do it in the book. But you could have just, instead of writing w, you could have written, or w squared, you could have written k over m here, written k over m. And your characteristic polynomial would be r squared plus k over m equals 0. And then you set it equal to 0. Okay. Now from this, we can read out our alpha. Remember, there's an alpha and beta here, right? Alpha is whatever's by itself, and beta is whatever's multiplying the I. So then we can find the general solution, which we now would call the complementary solution. It's a C1 times e to the alpha. Alpha is 0, so it's just 1, times the cosine of beta, which is w, times the variable, plus, again, e to the alpha, which is e to the 0, which is 1, times C2 sine of, again, beta times t. And that is the general solution, right? So pretty straightforward. And again, you don't have to use w. I use w because that's how they do it in the book. But you can derive the same solution just using w equals the square root of k over m, or w squared equals k over m. You would get the same solution. Now, as I mentioned, as it is written right now, so I mentioned this in the previous video, it's not obvious that that we can rewrite this just as one sine function or one cosine function. Okay. We'll see how to do that later, but right now it's not obvious. However, there are some things that we can tell from this general solution. First is that there is a period. How do we know there's a period? Well, both cosine and sine are periodic, right? Both have period 2 pi, right? So what's the period in this case? Well, the formula for period is 2 pi, if you remember this from trig, divided by whatever's multiplying the t. In this case, whatever is multiplying the t is w, right? So our period is given by 2 pi over w. And as you remember from the previous video, the period is just the distance between any two peaks or any two valleys, right? So think of it that way. Okay, so we can read that even though we can't see immediately that it's a single sine or cosine function, we know that this solution has a period given by 2 pi over w, where again, w equals the square root of k over m. Now, here we can see why when k, right, gets larger, and this is spring stiffness or spring coefficient, right, why that makes the period become smaller, right? Because if k becomes larger, w becomes larger, and if w becomes larger, 2 pi over w becomes smaller. Right? So that's where we get that 2 pi over w, and that's where we get that as k becomes larger, the period becomes smaller. Right? So the distance between any two peaks or any two valleys becomes smaller. Now we also have a frequency. Frequency is given by 1 over p, which in this case is just w over 2 pi. Again, w is always the square root of k over m. Now, the period is not something, the frequency is not something that I'm going to talk about a lot, but it's very important, especially because these sort of problems or situations with simple harmonic motion or just more generally periodic motion arise a lot when you're working with sound. Right? So we gave you an example of a vibrating string. When you work with sound, sound is measured in frequency. So it is important to know what frequency is, and that's why I mentioned it here. But for our purposes, we're mostly going to be talking about period. Now, in terms of what frequency is, remember that from trig, that sine or cosine, you can think of that as a graph, which is rotating around the unit circle. Right? So the frequency would be how many rotations do you complete per unit of time. Right? So if you wanted to give it an interpretation, you can think of it that way. If not, don't worry about it. But I do want to mention it again because it's important. So that's the information I can see just from this general solution. Right? Now let's actually go ahead and set up an example. So example 2. A mass weighing 2 pounds stretches the spring 6 inches. At t equals 0, the mass is released from a point 8 inches below the equilibrium position with an upward velocity of 4/3 feet per second. Determine the equation of motion. So what things do we know? Well, based on this problem, there's no damping and there's free vibration. So we know that this differential equation is going to be modeled by that this system is going to be modeled by the differential equation x double prime plus omega squared x equals 0, where again, omega squared or omega equals the square root of k over m. And then omega squared equals k over m. Now, there are some things we have to find. In order for us to find a solution, we need to know what k and m are. Right? So those are two things that we have to find if they're not given. And I don't think they're given in this case. So we're going to have to find the proportionality constant k, or the spring stiffness. And I have to find m. Now we also have initial conditions, right? If we want a specific solution, right, this is second order, right? So we're going to need 2 initial conditions. So what are the initial conditions in this case? Well, we're given an initial position because it says that the mass, so first a weight of 2 pounds is attached, right? And it stretches the spring 6 inches. So that's at equilibrium. Afterwards, we stretch, right? We pull on the string 8 inches below equilibrium. Sorry. So in our picture, we're pulling down 8 inches. Right? And then we release, or in this case, give it a push or pull. Meaning that at x equals 0, remember x is position, we're starting this system 8 inches below equilibrium, that's positive 8 inches. We also know the initial velocity, right? It would be 0 if we were just releasing this. However, we're saying that we're not just being releasing, we're actually giving it an upward velocity of 4/3 feet per second. Let's think of pushing on this when you release it. Right, so here we're given an initial velocity of 4/3 feet per second. Now, let me say something, that the units here are all over the place. We have inches, we have feet, we have seconds, which is fine. We're usually going to be working with seconds. We have a force of weight given by pounds. Usually we're working with newtons, right? So there's units are all over the place. So one other thing we're going to have to do is make sure that all the units match. But then when we have all this, if all the units match, we find K, we find M, we have the initial conditions in the matching units, and then we can go ahead and find the general solution. Okay? So we're going to do that in the next video, just so that this video stays not too long.